Hello, and welcome to this workshop on Karma, LookDev, and ground truth rendering in Houdini. My name is Valentin Kozin, and I am a lead technical artist at Xbox Studios Rare. As part of a game development pipeline, we tend to use a lot of different content creation packages like Houdini, Unreal, Maya, Substance, and many others. One of the things that becomes very useful when an artist is working across all of these packages is that you want content to match up between these different packages. One of the things that is useful is being able to get visual parity between the different viewports. And this might seem like quite a difficult challenge, but what we're going to do in this workshop today is show you a practical example of how to create a scene in Unreal Engine 5 and then port that scene to Solaris in Houdini. And we're going to light it in exactly the same way. We're going to replicate the geometry in that scene, and we're going to render it out, and we're going to try and get the Houdini Karma render looking as close as possible to the Unreal Engine viewport. And finally, we're going to talk a little bit more about why this is useful and some of the workflows that this unlocks for us. So we're going to start with a new Unreal Engine 5 project. Just created a new folder for this workshop. Houdini Workshop is the one that I made earlier. And in here, we're going to create a brand new level and very imaginatively call it Workshop Level. And as we jump in there, we're going to see absolutely nothing. And I'm going to minimize myself. Hello. So inside Workshop Level, we have nothing. So let's add a few things. And what we're going to do here is build a very, very basic environment that we're then going to try and replicate inside of Houdini. So what we probably want to start with is directional light. And we probably also want a sky atmosphere, which is this guy. And this is quite nice because we now have something to light the world with. So especially if we let's move the light to the origin. And if we raise it up by 20 degrees, go the other way, minus 20 degrees, we now have a sunlight and we have a sky. This is a nice lighting environment that we're going to then try to recreate inside of Houdini, and that's going to serve really well for look development. So what we're going to do next is give ourselves something to light. And we're going to keep things very, very basic and simple. I'm going to start with a standard cube shape. And let's give ourselves nice and easy numbers to work with. We're going to stick that here into the center of the map. And I'm just going to unlock the scale. I'm going to stretch it out a bit. I'm going to say this is going to be 20 by 20. Unreal is Z up, we got to remember. And Houdini is Y up, but that's going to be extremely important later. And I'm going to add one other thing in here. And what you might need to do is open settings and tick show engine content, because otherwise you won't see the default engine content. And what we want is the color calibrator, which is this guy that we're going to plonk right down here. We want it to go in the middle, and we want to sit on top of our cube. And there we go. Nice little test asset for us to use. Now there's something missing from here. You might be guessing what it is by now, and that's the skylight. With the skylight added, what that is doing by default is it is capturing everything that is more than 1,500 meters away from this point, and it's turning it into an HDRI map, and it's using that as image-based lighting. We can see exactly what's in the skylight, which is all this stuff. Now, what we would like to do in this case is, if we're replicating this lighting scene, in principle, all that we really need to do is we need to set up the directional light exactly as it is here, and we need to set up the environmental light. For all intents and purposes, both in Unreal and in Houdini, our scene will just have these two lights. Now, Unreal is making it, with this specific setup, a little bit more difficult because it has this idea of sky atmosphere and an atmospheric light. And in fact, what you'll see happening is that our directional light is technically white, but this, you'll notice, is not a white light. It is being tinted by the sky atmosphere. So we're going to do a little bit of trickery to make a slightly simplified setup. So we're actually going to have two directional lights. And what we want to do is one of them is going to be only an atmospheric light. And we're going to turn off its lighting channel so it doesn't affect the real world. And we'll call it light atmospheric. The other one we're going to call light world. And now, if we hide light world, we can see we still have our sky, but we don't have a directional light. We can turn this one on separately. So we've just separated our lighting levels. And this guy is not getting his color messed with. The other thing that we'll want to do is Unreal is also adding this sun disk into the sky effectively, which it's not actually using to light the world as such. You don't get the environment light actually casting hard shadows from the sun that's in the environment light. But in Houdini, that will be an issue. So we want to get rid of that disk. And we're just going to do that by reducing the source angle of the atmospheric light. And nothing happened. And that's because I need to actually turn off this one from being an atmospheric sunlight. So there we go. Now they are both properly separated and we can do whatever we want with them individually. We can spin them around independently of one another. It's a very useful trick if you're doing time of day systems in Unreal as well. So now that we have that, the final bit of setup that we're going to do is we're going to add a camera. So I just want a normal bog standard camera actor. I'm just going to grab it here. There we go. That's our camera actor. I'm going to put it somewhere here, I reckon. Let's have a look. It's field of view is 90 degrees by default. Let's zoom in. Yeah, that's a good shot. And so this pretty much defines our parameters. Like we want to replicate this exact view in Houdini, and we want to see how close we can get to it. The way this guy specifically is set up, the color calibrator has a gray ball, a chrome ball, and then it has two clear coat balls, which is those guys. I'm not going to be going into the intrinsics of setting up those specific clear coat shaders in Karma. They're not going to look exactly the same. It's the process and where we get to with it that ultimately matters. Now that we've got all of this, Unreal Scene, how do we get this into Houdini? Well, we're going to want to start exporting a few things. If we just had a simple diffuse metal roughness and normal map, we would have just very easily been able to export this into Houdini. Unfortunately, it has these little individual materials for all the different parts of it. But what we can do is, if we go into Tools and we do Merge Actors, we can export this with effectively baked PBR maps. So to do this, we'll go into this Merge Actors tool. And you can turn off Generate Light Map UVs. We don't really care about that. What we do care is Merge Materials. So if you go into Material Settings, so we want the normal map, we do want the metallic map, and we do want the roughness map. Those are the main ones that we're after. Obviously, the base color, I think this is going to give us by default. The other main thing to change here is the LOD selection type. By default, that's use all LOD levels, so it will export multiple LODs. And what it actually doesn't tell you is if it's exporting all the LODs, it's not going to bake the materials down. It only bakes materials down if you export a specific LOD, which in this case, it's going to be LOD 0. Sure, let's reuse Mesh Light Map UVs. Cool, let's do it. And now we want to save, well, we want to pick where we want to save this. So we're going to save this into our Houdini Workshop folder. And we're going to call it SM Merged Workshop Calibrator. And there we go. Now, this hasn't given us the very best UVs, but for this specific thing, it'll work fine. But the important thing is we've kind of got all of the data that we need here and all of the different roughnesses, and we can export that out into Houdini later. In fact, let's do that now. These now still only exist as U assets in Unreal, but we can go export. I'm going to want to go to my workshop folder, and I'm going to save these into here. And I'm going to untick collision. And we do the same for the textures. And it's just going to save them out as TGAs, which is fine for what we're doing. Again, probably if you're doing this for real, if you actually want to visualize some asset, 9 times out of 10, you're going to be having a PBR texture mapped asset. If you do need to recreate some materials, if you do have some complicated material layering, this is a cheap and easy way to just bake that out. So that's all done now, and we'll be able to import that in. There is, I think, only one other thing, that's to export our skylight. We are going to place a cube capture. Scene capture cube, that's the one. I can never remember what this thing is called. And in spite of its name, this is actually just another camera. And we're going to stick it right above the center of the world. And what we want to do is create a new textures cube render target. I call it workshop skylight. And we're going to assign this as the texture target. Now, if we open it, we can see, ta-da, we're saving the scarlet into here. We can make this a little bit bigger, 1024. We actually don't want our floor and the color calibrator in here, so the easiest thing to do here is just to switch the primitive render mode to use show only lists. And that's what we want because we don't actually want any of the objects in the scene to be rendered into this. We only want the sky. I'm going to save that and then right click on that and create a static texture out of it. So this is again quite nice because like with the merge assets workflow, this is just baking out whatever you have in your level. So you could be using the sky atmosphere, you could have your own crazy custom skybox that's lighting everything. You could even do this as part of a level, and you know, if you have an object in a room with lots of lights and other things and you want to visualize what that thing looks like in that room, you can still use this process and capture the environment of that room. And now that we have this, we can again just go and export this out and save it as an HDR texture. And that's it. That's all we need to do. For peace of mind, you can actually switch your skylight in Unreal to go from specified cube map to this one that we've just exported. And you can kind of see if you switch between them, it's exactly the same lighting. There's no difference. So that's it for our Unreal portion so far. So here I've opened a new instance of the brand new Houdini 19.5. This is what we're going to use to recreate our scene. To do this on hard mode, we're going to do this in LOPS rather than in SOP. You don't have to do this in Karma. You can entirely do all of this in Mantra, but we're in 19.5. We can do this as a very quick kind of LOPS tutorial. And don't shout at me, I'm still quite new to LOPS myself. So first of all, let's create a box and add it to our scene. And this is going to be a base that we created in Unreal. And we're not going to do anything fancy here. We're literally just going to repeat the process that we did in Unreal. It's 20 in X and Z rather than 20 in X and Y. That's our box again. And we want to assign a material to it. So one of the easiest ways to do that is to create a material library. And we can go in here. And again, just to be fancy, we can do material X standard surface. And now we want to actually go back to Unreal and double check what is the material on this guy. And so we can see our color is full white and our roughness is 0.6407 to a PBR. So we set our color to white and we set our specular roughness to 0.6407. Now change this to, let's call it ground matte, and it matters what we call things. So let's call this ground. Since we're working with LOPS, it's worth adding a scene graph tree view to this as well. So now we can see our scene graph, and this is our ground mesh. And here is all the materials that we've got. We also need to apply this material. We want to, well, let's remind ourselves of our materials. We have ground matte down here. I'll pick that out. We want to assign it to geometry, and the geometry is /ground. And now this guy is going to be a little bit more white. Just to double check that this is set up correctly, we want to go into the ground material and try and change its color. And if we set that to magenta, it changes to magenta. Let's add some Karma render settings. And this in particular allows us to switch, for example, to XPU engine and adjust other things if we want to. This is now path tracing on the GPU. There's not a lot to path trace here yet. Let's give us the other thing that we're after, which is our color calibrator. Again, there's a few ways to do this, and we could go back into our normal SOP contact. You can also just create a SOP network inside of LOPS. In this case, that's going to be SOP create. We're going to go into here, and we're going to add our little color calibrator, and that's this guy here. It's a bit big to start with. That's because Unreal has everything in centimeters. Converting from centimeters to meters, we just multiply it by 1/100th. And now it is about 1 meter high, which is what we were expecting. There's not a lot else we need to do. We're not seeing him yet, and that's because we need to merge this network in with this one. And we still don't see him yet, and that's probably because we need to move him up. As you recall, in Unreal, he is 90 centimeters off the ground, which means that in Houdini, we want to stick him at 0.9, and there he is. Now, we need to apply materials. Do the same thing that we've done so far, which is apply a material library. And since we've baked it all down, there's only one material to create. So, same as before, we'll just create a Material X standard surface, but this time we're going to hook up some nodes to it because we need to do some logic. So let's begin with a Material X image. And this is going to be our base color. And before I go too much further, let's just rename this to calibrator material. And when we go to material library, let's do the same thing that we did before. We grab the calibrator mat VOP, we assign it to this guy, which we should probably call calibrator as well. And there we have it. We've got colors, and you should know what to do by this point. We can grab material X image again, and we want to grab our material roughness specular. Now, one thing to note is if you're used to principal shaders in Houdini, you're probably used to there being a little automatic or linear drop down. You don't have that in these nodes. I mean, there's a linear here, but this is your filtering. It's closest linear cubic, not what we're talking about, whether a texture is in gamma space or linear space. The base color is usually going to be in gamma space, and this is connected in and it's loading in fine, so that's good. Metallic roughness, we want that in linear space. How do we make sure that we don't get it in gamma space? That's the difference between having a color signature and a vector signature, or a float signature for that matter. So what we want to do is switch this to vector 3, and that's going to ensure that Karma loads it in as raw values. So next we need to split this out, and if you've used VOPs before, you might be tempted to do vector to float. That's not quite what you want, though, because we're doing Material X, so we want to make sure we're using all Material X functions. So in Material X, it's actually separate vector, and that's what we're going to use. From this, we can plug our X into metalness, and we can plug our Y into specular roughness. And there we have it. Now we have correct roughness on these guys. And as you can see, there's our chrome ball and there's our diffused gray ball. The next step is going to be to add some lights, and we're going to begin with our skylight, or dome light as Karma would call it. It's pretty much as straightforward as you'd expect. We add it in, we assign a texture, which is the HDR that we've exported. We plug that in, there we have it. We have the same lighting that we had in Unreal, well, minus the directional light. If we go into Unreal, our chrome sphere is at the front of the calibrator and it's facing the sun. Whereas when we're here in Karma, the sun is in this direction, it looks like, and our chrome sphere is facing away from it. So the question is, do we rotate the calibrator or do we rotate the HDRI? Well, the trick is going to be in lining up our completely different coordinate systems. So here we've got Y up and we've got X facing in the direction of the sun. And in Unreal, if we press G again, we'll see we're Z up. And we've actually now got X facing away from the sun. X is the common vector that's always on the horizontal plane, so that's our point of reference. So we want to be in a situation where the chrome sphere is facing in that direction in minus X, and the sun in the skylight is also in that direction across minus X. What this tells us is our chrome sphere is facing in the minus X direction, so this is actually correct, and all we need to do then is rotate our dome light. Transform, rotate on the y-axis, and now it too is facing along minus X. Everything we've got in here so far is adhering to the coordinate system conversion. But we've got two more things left to add, and that is the directional light and the camera. And those aren't as easy. So let's start with the camera, because that's going to be the easier one to debug, and it's got the more axes of freedom. If we get the camera right, the directional light should be pretty straightforward to do. So we're going to add it in here, and we're going to merge it into everything else. And we don't need to be rendering, so let's switch to wireframe view. That means it's a bit easier for us to actually see the camera. What I'm going to do is I'm just going to add a new folder in here that will allow us to set our Unreal transform. We're not going to call it Unreal parameters because we're going to want to also convert the FOV. And we don't want this to be tabs, we want this to be collapsible. And in here, we're going to want a few things like position, rotation, and we're going to add a float for FOV. We apply these, now we've got these guys. In Unreal, let's just go and copy our values across. So this is the data that we've got in Unreal, our FOV, our rotation, our position, and our job is to then fill in all of the actual Houdini data with all of this stuff. So we're going to create some keyframes. That was just me alt left clicking. And we're going to change the language of these to Python. And if we then press Alt E, which is the same as right-clicking and doing edit expression. And let's grab this node. And in this node, we have Unreal pause is Houdini vector 3, and that's going to be... Now, what's the Houdini position going to be? Well, we know it's Z up, so we got to swap the Z and the Y, and we know that Unreal is in centimeters. What I originally did is then return Houdini pos 0. Then anytime we have to update this function as we copy paste it across the 3 channels, we then have to manually select which index we want. But what you can actually do is you can get the current vector ID, and this is, got this I think from the actual Houdini help docs. You can get the component index that we're currently in, which is quite fancy. And then if we stick that in here, this automatically becomes 0. And that means we can apply this, and we can go through and we can paste this in and get all the values automatically. So now we can see our camera is a little bit to the back and behind the calibrator relative to the sun, which is exactly where we want it to be. And now we just needed to aim at the calibrator. So let's give it a go. So grab the current node, and let's grab the vector ID as well, since we know we're going to need it. And then we want to get the rotations. And from those we can create an Unreal rotation. And from the Unreal rotation, we can create a quaternion. In fact, we're going to create 2 quaternions. And there's another thing that we're going to have to account for, which is the fact that when I create a camera in Houdini and its orientation is at 0, if we go to Unreal and we create a brand new camera, its rotation, as we can see with the cube capture as well, is along the x-axis. So even if we have our rotation being mapped perfectly correctly, we need to account for the fact that the forward direction of the camera is different. It just means we have to apply another rotation to it, which is specifically to rotate that camera to be facing down the x-axis. We just need to create yet another quaternion, which is, I'm going to call this the face x quaternion. We'll just set it to angle axis, and we're rotated by -90 degrees around the y-axis. The Unreal quaternion we get from the Euler rotations, and then the Houdini quaternion is kind of a swizzle. And now all we need to do is compose our quaternions. We're nearly there. From there we want to get a vector of rotations, and we do the opposite of set to Euler rotation, which is quaternion extract. To fill this specific channel, we just get the correct index out of those. And we copy this, we hit apply. I made a mistake. This is not rotation, it's rotates. And that is giving us a value that is probably correct. So fill these in, and there we go. Now we have rotations, and look at that. We can see our camera is now indeed looking at the calibrator as we wanted it to. In Unreal, we have a horizontal FOV of 62.7. And here we have currently a focal length of 50 rather. If you go to the side effects Houdini website, there is a really good help page about how to match Houdini camera lenses to the real world, which tells you exactly what all these different values are and actually what the relationship between the horizontal FOV and the focal length is. You can work this out just from those principles. TOA. That means we've got tan x equals opposite over adjacent. We know that that's FOV divided by 2. Opposite is divided by 2, and adjacent is focal length. We do the usual kind of division substitution, and we swap these around. And since this is an expression, we don't need this, we just need the result of these guys. Hit apply, and that's our focal length of 17.1919. Hopefully that is correct. Compare that to Unreal. And I'd say that's a pretty good match. I think we're pretty spot on there. All we've got left then is the directional light. And this one just has -20 and intensity is 10 lux. So we're going to add this in. I'm going to set its intensity to 10, and we're going to do the same process. We're going to add a new folder, and that's going to be Unreal parameters. We set this to -20. And then we go to the transform and set a keyframe, convert that keyframe to Python, then Alt-E. We want to go back to the camera and just grab our code from these guys, and we can just copy paste that wholesale. Oh, look, We have our directional light. And that's pretty much it for the scene setup. We now have fundamentally exactly the same scene in Houdini and in Unreal. What we have here in Houdini right now is a perfectly linear rendering of the image. Probably this is even a bit unfair, because if you're going into this by default, you probably see something more like this. You've got the eye adaptation on, and you sort of compare these two, and this is way different. So first of all, we don't have eye adaptation in Houdini, so we want to turn eye adaptation off. These tone mapping approaches can be quite different between different software packages, but actually there is a way to standardize it. And that is one of the things that the ACES color pipeline offers, which is the Film Academy standard for handling color and maintaining consistency between different packages and different pipelines. Unreal actually uses ACES by default already. That is what you see being applied here is the ACES reference rendering transform, which is a neutral film type look with linear tone mapping. As if I look at this sky here, you can see all of these colors here are just burnt and very orange, and you're getting that sort of distortion here, which you don't get here. This is all much more subtle and much more nicely muted. And if you're doing rendering and compositing, you have tools in Houdini for changing color correction. You actually have that here in the viewport as well. So you can bring up the correction toolbar. And what you might know is that by default, you have kind of a LUT and gamma options here, and you can apply your favorite LUTs, and you can change the gamma for this. So I guess I was lying because that's not strictly linear. This would be strictly linear. What we had before, it is at least applying the sRGB gamma curve. But you also have the Open Color IO option here. And if you go into Open Color IO, you get a lot more options here for different kinds of display outputs. I believe this is actually applying also the ACES reference rendering transform. You can see we don't have that burn here anymore on the sky. But the colors are also weirdly vivid. So what's going on there? Well, the problem is that what we want to do is get a little bit more control over this, because there's stuff that Unreal is doing in here, and there's stuff that Houdini is doing in here, but they're not matching up. And the cool thing is that we can get them to match up, and we can get them to do pretty much exactly the same thing. What you want to do is find yourself the OpenColor IO configs for ACES. OpenColor IO is an open source framework for working with color, and it allows these transforms to be standardized and ported across between different packages. In this case, we want to grab ACES 1.0.3, and effectively you just want to download this repository, whichever way you want. You get the OCIO config out of this, which you want to stick in some fairly well accessible place like your C drive. I've just literally got my C drive and then ACES 1.0.3, and if you open up the config.ocio, you will see a little bit of what's in there. So this is a YAML file. There's a lot of stuff here. Effectively, you have a few different roles, and these define what color space you want certain things to be done. Rendering is generally done in ACES CG, which is the slightly smaller one. Scene linear is defined as ACES CG, and you have a utility raw, which is effectively like the linear. You're not doing any transformation to get that into a different color space. You just want to read the raw value. Past your roles, you have your displays, and that's the stuff that when we go to Houdini and when we look at the OpenColor IO things, we can see displays, and we can see different views for each of those displays. It has a single ACES display, and then you just have a few different views which cast that output for different types of monitors. So you define those here, then you have active displays and active views, which is the ones you can actually use. Really, the important thing are these bits, because at the moment, Unreal is still working in sRGB. So what we want to do is we want to edit these to make sure that we really only have the color spaces that we care about. I'm just going to open the one that I made earlier. I've deleted a lot of the color spaces further down that I don't need, but you don't need to do that. The important thing is this bit here. Effectively, I've changed most of this to just be using linear sRGB as our rendering space. We really only need a few views, and one of them is the tone mapped sRGB, which is the ACES output sRGB color space. And then you have the input generic sRGB texture, which is literally just assuming we're in linear sRGB, but then it's applying the 2.2 gamma curve. And there's utility raw, which we're just interpreting as linear. And that's going to be our three views. Making these modifications, I'm just saving that as a separate config underscore unreal.ocio. Close our version of Houdini, open the Houdini environment, and we're actually going to create an entry for OCIO, and that's going to be config unreal.ocio. And this should, when we run Houdini, replace that OpenColor IO set of default settings with these ones that we've specified, and it's going to move it into an sRGB-based workflow. So here we are loading back into our scene, and we can see it's looking a little bit different already. If we look down at the color correction toolbar, we can see that this has changed now. Because we have an OCIO config specified, we now have this toggle. We can either turn off OCIO entirely and we go back to fully linear rendering, or we can turn it on, have our aces display, and here we have our three views that we've defined, which is sRGB tone mapped, sRGB, and linear. So if we go to sRGB, this is what we were seeing before with that slight burn-in on the sky. If we go linear, that's our fully linear, sort of extremely burnt CGI look. But now if we do sRGB tone mapped, we're getting that much nicer, softer sky that we did in Unreal. And we don't have the wild, extremely vivid colors anymore. And if we load up Unreal again, we can see that these two are extremely similar now, in fact. We're now getting to the point where actually our colors are pretty much the same. Most of our difference is in lighting. The square pattern here is quite flat, whereas here we've got more shading. And that's actually down to us not having the path tracing. Unreal's Lumen not being quite as accurate for small details. So if we turn on path tracing, we get, again, more of a match there. And this is getting pretty close. And like I said, we're not focusing on the clear coat spheres here, which have that whole more complicated material setup. If we go to our preset camera views, we can see exactly how close this is, which is, that is visibly, noticeably the same scene and pretty much the same brightnesses and everything. And that's us, to be fair, pretty much done. And there's one other thing that you can do, in fact. There is an OpenColor.io plugin, which is in beta for Unreal. I have this turned on by default. You might need to click it and turn it on. But this actually allows you to load your OCIO config into Unreal. And you can literally use the exact same config and the same color transforms in Unreal as you're doing in Houdini. You can go and create an OpenColor.io configuration. And I've created one earlier. You literally just point it at where your OCIO config that you've created is, and you pick out which color spaces you want to have. And once you've done that, you can go into your view mode menu, and you actually have a color management OCIO display bit here, and you can turn this on and off, and you can select which color space you want to convert from and to, and this will actually apply to your viewport. So in this case, this is now pretty closely matched to Houdini, just on account of the fact that it's using that OCIO look. And now this is literally the same tone mapper. That leads us to the next question of why is this useful? This is one reason that I think is particularly interesting. Consider this chart. I've rendered the famous Sponza atrium in 4 different versions, and this is rendered in Karma, and I've not changed anything about the render settings itself. There's nothing different here about how many bounces the light has or how it propagates, but there is a difference in the scene if you want a hint to start guessing what we're exactly changing here. But there is a difference in the exposure of the camera. The difference is the albedo. So if I uncover these, you can see that what we're changing is the brightness of the surfaces off which the light is bouncing. The trick that we're doing is we're doing a very specific kind of metering. What's happening is that we're locking onto this center of the courtyard. We are forcing that to be a middle gray in each picture. And what you're seeing is the fundamental difference that albedo has on the lighting of a scene when you're actually using path tracing and when you've got physically based lighting. Depending on your exposure and depending on how you're setting up your environment and your colors and your textures, this is actually going to have a fundamentally different effect on your look. If you're creating this environment, if you're creating a procedural Sponza atrium with textures and everything that's being generated inside of Houdini, it actually would be quite useful if you could see what that's going to look like in Unreal while you're doing it, and you can see the light levels and change the colors and know that what you're actually going to get ultimately in your game engine is going to be similar to what you're doing here. Something else that this is useful for is the development of complex materials and complicated shaders. If you're doing look development on things that you want to get close to physically accurate, but in ways where you can't model them in a physically accurate way in Unreal, having a ground truth preview of Unreal scene becomes extremely useful. So this is an example inspired by the technical art of Uncharted talk from SIGGRAPH. They needed to improve their moss rendering, and what they did was actually take a ball and cover it in moss and render it out in Arnold. And then they matched their in-game shaders to behave how that physical moss that was made out of little clumps behaved in relation relation to light. So what I've done here is I've created a moss ball, which is done quite simply by taking a sphere and scattering a lot of very, very small polywire tubes like this across it, and we're assigning two different materials to it. There's a very handy feature in LOPS, which is that when you're using the SOP create node in LOPS, you can add path attributes to your primitives, the path that you type in. So in this case, I'm creating an object called moss and an object called sphere. It's in graph tree. So I've now brought in that moss test object, and it actually has sphere and moss under it. This means that I can actually then sort of create separate materials for the sphere and for the moss, and I can apply them. In this case, I'm not doing anything particularly fancy. They're literally just, one of them is slightly darker green and the other is slightly lighter green. But when we then render these out, we get very particular kind of physically path traced shading like this. Because this is now in exactly the same color space and the same kind of, is using the same sort of tone mapping as Unreal is using, that means that we can use this as reference for building a shader, which will be much simpler. It's not going to be scattering millions of little points of geometry across a given material. Then if we get this kind of target look in Houdini, we can then start working with sort of traditional real-time rendering tools like shaders and material graphs and textures to replicate this and see how close we can get. So what I want to do to close out this workshop is demonstrate how this sort of approach of working with matching up viewports and color and lighting can then inform your LookDev pipeline. And I'm going to try and replicate this material and see how close I can get to it in Unreal. I'm going to fast forward through this, so bear with me. And there we go. I'm just going to go over very briefly what I did. Because we still have the cameras synced up between Unreal and Houdini, we can go back and forth and do a direct comparison. Same shot, same lighting. This is Houdini, and this is Unreal. And as you saw when I was working on this, I was going back and forth a lot, comparing what these guys look like. And this is the material graph that I ended up arriving at. Effectively, I'm creating the noise texture to match what we saw in Houdini based on some default noise textures that are already in Unreal. And then I'm using a Fresnel function to add this darker rim around the edges where we start seeing the strands of moss from the side. And I'm modifying the specular power as we sort of get here into the specular highlight to get this look of the shadows that the strands are casting that we can see in Houdini. I'm also playing around with ambient occlusion. This is the trick that Naughty Dog used, which is actually using ambient occlusion with a Fresnel filter so that surfaces on the outside towards the edge kind of get seen more as a solid surface, and the ones that are in the middle looking down into this shadowed area between the strands of moss. I guess this is a slightly different moss setup. This is a bit more hairy. So I'm using a little bit of Fresnel to give it darkness variation here and there. But one of the main things for me is that we have this sort of dark fringe. I guess unlike real moss, we've not set up any subsurface scattering. So light isn't scattering through these hairs when we see them edge on. We don't have that glow effect. Instead, we have this sort of quite dark stubble. And to match this up, what I realized, part of what's happening is that we're looking at these little strands side on. So they're not reflecting light that's coming through as if they're facing towards the light. They're reflecting that light as if they're facing towards us. So what I'm doing is I'm interpolating the normals from the vertex normal to the camera normal, which is to say facing us at the outer edge. And there we go. And so if we sort of detach from this, we can see, and to be fair, I haven't really considered the front view. So if you compare that, you'll see from the front in Karma, we have a little bit more of the shadow casting that we can see from these strands, which is making the surface a little bit darker. And that's something we can go in and we can maybe even add a little bit of parallax or ray marching to this texture. But ultimately what we're kind of interested in is capturing the sort of the macro behavior of this surface without having all of the micro polygon details that we're modeling in Karma. And I think this is a pretty good start for that. And that brings us pretty much to the end of this workshop. Well, thank you for bearing with me, and I really hope you found this workshop interesting and useful, and that you will find many things that you can apply in future work. Enjoy the release of Houdini 19.5.